Okay, so let me do the screen share. Okay, so thanks to the students who attended Yellow's tutorial, and I hope it was helpful for him. So in the last class, we were looking at the Ampere's law, and we did several examples on Ampere's law. If you remember, we saw the toroid, we saw the solenoid, and we saw a few more examples on application of Ampere's law. Okay, and then we went to the definition of magnetic flux density, which is very similar to the electric flux density, D, and here it is B. And their definition is psi is closed surface integral B bar dot ds bar, and B is equal to mu h. And it is very similar to, in the electrostatics case, it is very similar to your electric flux, which is psi is equal to closed surface integral D bar dot ds bar, right? So flux amount of electric flux density passing through a surface. Here also the amount of magnetic flux density passing through a surface is called as the magnetic flux. In order to identify, sometimes people use psi m and psi e. And then the magnetic flux density is mu h, and the electric flux density is d bar is equal to epsilon e bar. And E is the permittivity, and here mu is called as the permeability of the material. So these are the two very important properties of a material: permittivity, permeability. These are the two important properties of a material which defines the material. Okay. Besides this, there are two more properties. So this is one, this is two, and third one. Can anybody tell me what is the third property that can define a material? Yes, Mr. Abdullah Rahim Al-Mushrif. Can you tell me? The third. So I said, yeah, no, this is just a general question. A material, its properties, how it behaves in our technical terms, in our engineering terms, or I would say in our science terms. It is defined by its permittivity, it is defined by its permeability, and it is defined by its
density, maybe.
Density, no. We have seen this. See, this is epsilon, this is mu. We also saw this. What is this?
Conductivity, Doctor.
Conductivity, yes. So conductivity. And you have another very important term, F, which is nothing but frequency. This we will see it later, how frequency can change the property of a material. This is later, but at least we have come across all these three properties: permittivity, permeability, and conductivity. Conductivity we have been studying right from electric circuits. So now we are studying permeability. So now altogether, these are the three properties along with, this three parameters along with this frequency that completely defines any material. Okay, it completely defines any material. Now we have seen for permeability, it is called as mu, and it's a constant. It is 4 pi times 10 power minus 7. And again, we have the permeability defined as mu, which is equal to mu r mu naught, which is mu r is called as relative permeability. It is called as relative permeability. And this is the permeability of free space, very similar for the electric circuit, for the electrostatics. Epsilon is epsilon r, epsilon naught. So this is called as relative permittivity, or there is a very common term used for relative permittivity, which is a dielectric constant, very common term, or it is the relative permittivity. And then in order for the analysis, their definitions very similar. So mu r is 1 over chi m. Here you had epsilon r as 1 over chi e. So where chi m is magnetic susceptibility, here chi is electric susceptibility. And this is actually a thing, as I told you, it's a measure of how your material behaves when it is subjected to electric field or when it is subjected to the magnetic field. And if I substitute this in the B, so you will get as this one. So where this is called as M vector, which is called as magnetic polarization density vector, which is similar to here P bar, the polarization density vector. So electric polarization density vector, P bar. Okay. So again, this is a measure of how good is your material, with respect to the electric field. It can measure. So here also, how good is a material with respect to the magnetic field. Okay, and we know it very well. For free space, mu r is 1. Or vacuum, it is 1. Similarly here, we know it very well. For free space, epsilon r is 1 because epsilon naught, epsilon r, this is nothing but it is 10 to the power of minus 9 over 36 pi. Okay, so this is a little bit introduction about the magnetic flux density. Now, therefore, we will just now move ahead. And now we have another law that I am defining besides the Ampere's law. And that law is Gauss's law of magnetic field. Okay, so we have Gauss's law of electric field. If you remember, the Gauss's law of electric field is closed surface integral d bar dot ds bar is equal to the charge enclosed. So this is the Gauss's law of electric field, electrostatics. This is the Gauss's law of magnetostatics. And what does Gauss's law of magnetostatics say? That is the magnetic flux, because magnetic flux definition is b bar dot ds bar. And if I'm putting a circle here, that means I'm evaluating over a closed surface. So it says that the magnetic flux through any closed surface is equal to 0. So the magnetic flux through any closed surface is equal to 0. Or if I say it in this term, the magnetic flux density over any closed surface is equal to 0. Here, the electric flux density, through any closed surface, or evaluated over any closed surface is equal to the charge enclosed. But here it is 0. This is called as the Gauss's law of magnetic field. Now, a simple question arrives in our mind. Why is that? Why it is 0? Why the closed surface integral b bar dot ds bar is 0? Why? Why it is equal to 0? We can understand it by comparing these two. See, this is my electrostatics Gauss's law. This is my magnetostatic Gauss's law. The thing is, in electrostatics Gauss's law, our charge, an isolated positive or negative charge can exist. That means I can have a positive charge here, or I can have, maybe our sphere, I can either make it positively charged or I can make a sphere negatively charged. That means I can say that I can have an isolated positive charge and isolated negative charge. So for example, here, if I have an isolated positive charge here. Okay. Then if I enclose it in a closed surface, then what you will see, you will always see that for the positive charge, the flux lines are going out of this closed surface. So flux line goes out of this closed surface. Now let's come and look at the magnetostatics. So I am now taking an example of a solenoid. So this is my solenoid. And I am now looking at only one end of the solenoid. Now, and if I apply this closed surface at one end of the solenoid, then what I'm seeing? I'm seeing that some flux lines are going out of my surface, see? And some flux lines are entering. Some flux lines are entering. So the net B bar dot ds bar, flux lines, or I would say the magnetic field or magnetic flux density. So the amount of magnetic flux density entering this closed surface, which are these four lines, and the leaving this surface, these four lines. So what is the net value? The net value is C. But here, since a charge can stay isolated, so positive charge, your field or your flux lines can always be going out. And it's not necessary that your field lines will enter because it can stay isolated. But in magnetostatic or in magnetic field, the positive and the negative, there is no concept of positive and negative, but here we have a concept of north and south. They cannot exist separately. They cannot exist separately. And this we have been seeing from physics, that if you have a magnet, then the magnet will have a north pole and a south pole. See, a north pole and a south pole. And then if you cut the magnet, try to separate the north pole and separate the south pole. If you cut the magnet into two halves, then these two magnets will make own north and south poles. It will make own north and south poles. So therefore, what will happen is always, if you put a closed surface and if you try to evaluate this, you will have the magnetic flux line entering and the equivalent amount of magnetic flux lines or magnetic field leaving, so that the net is 0. So this is called as the Gauss's law of magnetostatics. I think it is clear. Any questions, guys? No questions? So shall we move ahead? Also, just one, 2 minutes I want to spend on another very important concept, which you guys need to know, is about the Ampere's law. Okay, it's about the Ampere's law. Yeah, let me talk about here. Now, or if I have the, let me just say, let me have the 13th lecture. Okay. So what?
Sir,
yes.
The midterm exam until which lecture?
We haven't decided. We will let you know.
Okay.
Okay.
Probably
So,
lecture 13 included, right?
yeah, most probably it will be complete electrostatics and complete magnetostatics.
Okay.
Okay. Yeah. So just 2 minutes on the Ampere's law. This is very important. The Ampere's law, guys, just think about here. Now for this infinite line, I applied Ampere's law. So because this was going to minus infinity and this was going to plus infinity, right? And I applied Ampere's law. And from the Ampere's law, I got the expression, which is H bar is I over 2 pi rho A rho, right? Yes. Now, my question is, this is for infinite. Suppose if I apply the Gauss's law to a finite wire, That means a wire which is only this much. And if I apply Gauss's law to this wire, so I put a Ampere's path, then what expression do you think your Ampere's law will give? Yes? What expression do you think the Ampere's law will give? Yes, Mr. Muhammad Al-Humaidan, can you tell me? Muhammad
Yes, Doctor, I'm thinking just 2 minutes.
Yeah, see, so here is the infinite line and you put an Ampere's law here, but here it's a finite line and still you are putting an Ampere's law here along this path, along this purple loop. So what expression do you expect? You will expect
the same, Doctor,
same expression, right?
for this limited area.
Yes, for the finite also you expect the same expression, but this is wrong because we know the expression of finite, it is I over 4 pi epsilon time of cos of alpha 2 minus cos of alpha 1. Remember, this is the expression. Wow, so here what is happening? It seems that Ampere's law is failing. Am I right? So this is, we are getting a feeling that Ampere's law is failing, but this is not correct. So Ampere's law is intact. Ampere's law is completely correct. Now the only thing is Ampere's law is completely correct. And works for all the practical cases, for all practical cases. Now, do you think this kind of wire can exist? Finite?
Yes.
Yes. Can it exist in our say in our practical case?
Yes, our practical case actually does not involve infinite wire at all, only finite.
Yeah, infinite doesn't exist, but can we have a finite like this, Mr. Humaidan, only this much size and carrying a current I?
Yes, we can.
No, I don't think so, because in order for the current to pass, you have to connect it to a source, right? So it will always be a closed path for a current. Do you agree or not?
Yes.
It is.
What about transmission line, Doctor?
Yeah, sorry?
Transmission line.
Yes.
I mean, it's applicable to this finite.
Oh, transmission line is different, because in transmission line, your current will be an AC current. It will not be a DC current. Here we are talking about a DC. Even if it is AC, Ampere's law will hold for AC also. But in the transmission line, still it is connected to a source, right? Still it is connected to a source. So whatever source it is, still it will be connected to a source, right? Something like this. So now let me talk about it. So it works for practical cases very well. And now the second thing which is very important for the Ampere's law is Ampere's law. We are applying the Ampere's law along this closed loop, right? But we need to also take care that your current must cut the surface enclosed by the Amperean, Amperean loop. This is also important. This is very, very important. This is how the Ampere's law is applicable. That it is not just the ring and you just enclose it in the ring. You also have to make sure that your current should cut the surface which is enclosed in the ring, which is enclosed in the ring. Now, Mr. Nawaf Al-Saleh, can you tell me how many surfaces are enclosed in this purple ring? I showed you this one surface, which is yellow in color. How many more surfaces you can make? Mr. Nawaf, you are there? Mr. Nawaf, you're not there. Okay, Mr. Taha Al-Kazim,
Yes,
tell me.
yes.
Yeah, I showed you one surface, this yellow color surface, which is enclosed in this purple ring, which is enclosed by this purple ring. Is this the only surface, or you can create more surfaces?
I think this is the only surface.
This is the only surface. How about others? Now I'm leaving the question open. What do you guys think? It is only this one surface, or you can create more surfaces?
I think there are more surfaces.
So how
Yes.
many? How many?
Infinite.
Infinite.
Ideally infinite.
Infinite surfaces which can be enclosed by this purple. Why? Yellow is one. Can't we have a surface something like this? Yes. Yes. And can't I have a surface like this, which is enclosed like a pot? Like a pot, and the opening of the pot is this ring. And can I have a surface like this? Yes. So in order to have the Ampere's law work, your current must cut each and every surface which is enclosed by your Amperean loop, which must cut each and every closed surface. That means it must cut all the infinite surfaces. Now for a finite wire, do you think the finite wire will cut all the surfaces? No, because if you see here, the finite wire is cutting only this black and this one. Is it cutting this surface? The third one? No. It is cutting the fourth surface? No. That's the reason your Ampere's law doesn't work for this finite case. For the infinite case, we got the correct answer. Why? Because if this is infinite, then all the surfaces which is enclosed in this ring, all the surfaces, this one, or this one, or this one, they will all be cut by your infinite line. So that's why the Ampere's law holds, and you will get the correct answer. And in practical cases, you cannot have a hanging wire, right? You cannot have a hanging wire by carrying current. Eventually, this wire will be definitely connected to some source. It will be definitely connected to some source. So therefore, if it is connected to a source, or if it is connected to a source with the help of a load, even when it is a transmission line, then definitely if it is closed, then all the surfaces which is created by this Amperean loop will be cut. And therefore the Ampere's law will hold. So this is something which we should know about the Ampere's law. And that's why we say that the Ampere's law is applicable for all practical cases, because the Amperean loop will definitely cut, the current which is passing will definitely cut the surfaces, all the surfaces which is enclosed in the Amperean loop. Our Amperean path. Okay, so this is very important. We should know about this Ampere's law applicability. Okay, so now let's go to our next part, which is our magnetic potential, and spend the remaining 20 minutes on that magnetic potential. Okay, so now this is talked. So therefore, now I'm summarizing all the laws that we have studied now. So we have now 2 laws, 1 and 2 laws of electrostatics, and we have 1 and 2 laws of magnetostatics. So the electrostatics del cross E is 0, which is coming from the conservation of electrostatic field. Integral form, closed line integral E bar dot dl bar is 0. And then del dot V bar is rho V. This is differential form. This is the integral form of Gauss law for electrostatics. And then, so any vector field, if it satisfies these two laws, then only it will be an electrostatic field. Similarly, any vector field which satisfies these two laws will be a magnetostatic field. So next is the Ampere's law. Del cross H is J bar, Ampere's law, and the Gauss's law of magnetic field, which is del dot B bar is equal to 0, or closed line integral B bar dot ds bar is equal to 0. And remember, you can use these laws to assure that your vector field is a electric vector field or a magnetic vector field. This is important because, you know, these laws has to be satisfied by them. Okay. So now let's go and talk about the potential. So very similar to your electrostatic case. In the electrostatic case, you have an electric potential and you have electric potential difference, and this electric potential, or the electric field which is existing in the region is responsible for this electric potential. So same idea applies here. So magnetic field which is existing in the free space or in any material, it will be responsible for the magnetic potential which will be in that material. But now here there is a little bit of understanding which we require, and this is coming from the mathematical formulation. Okay, so just remember these two mathematical relationships. What are these two vector identities? The first one is the del cross del phi is 0, where phi is your scalar field. This is a vector identity. Then del dot del cross f, divergence of curl of f, where f is any vector field, is 0. So you just make sure, remember these two identities. Okay. And now we are just following what we did it in electrostatic. So what we said in electrostatic, we said that E is equal to minus del V. This is coming from the electrostatics, right? Where V is the electrostatic potential. This is how I defined V. V is an electrostatic potential, and in electrostatics, it's a scalar quantity. It's a scalar quantity. Now, what we can do is we can just follow the same idea that we did it for electrostatic and apply in the magnetostatics. And therefore, in magnetostatics, we can also define a potential called Vm, which is the magnetic scalar potential, in such that my H bar is minus del Vm. Okay, and how to get this expression? We can follow the similar steps that we did to get this expression. So therefore, H bar is minus del Vm, where Vm is the magnetostatic potential and Vm is a scalar. And we can stop here. But now the issue is the following. The issue is your electric field is conservative. Conservative, right? Conservative, like our potential energy. If you go up, if you go up from the ground, the potential energy increases. If you come down, the potential energy decreases. So the net potential energy will be 0. Like this, it's a conservative. Closed line integral E bar dot dl bar is equal to 0. But magnetic field is non-conservative. Non-conservative. So this creates an issue in our mathematical formulation. See why? Because del cross E bar is 0, but del cross H bar is J, Ampere's law. Now let's put this expression. Let's put this expression and see here whether this will hold or not. So substitute in place of H minus del Vm. So we substituted minus del Vm. And we are getting as minus del cross of del Vm. Just now we saw this vector identity. What is that? Del cross of del a scalar. What is del cross of del scalar? It's, yes, it's, yes, guys. I know this is a little bit, say theoretical part, and the next, 20 minutes is all our theoretical part. But let's just try to understand and enjoy, why we are doing all these things. I just now showed the identity. See, del cross of del of a scalar is 0. So if you see here, del cross of del of scalar is 0. So what does that mean? That means if this quantity is 0, that means your right hand side is what? J bar. So your left hand side is becoming 0. So that means your right hand side is equal to the left hand side. That means J bar is equal to 0. Oh, what does that mean? Oh, that means this definition of scalar vector potential is restricted. Is restricted only to the region where J bar is 0. Why? Because as we told that all our laws must be satisfied. There should not be any inconsistency mathematically also, because yes, these are all, electric and magnetic field are all, they are all existing. But in order to put it on a paper, we are using vector calculus. But when we put on a paper, we have to make sure that there should not be any contradictions. And that is why we are doing this. And if you see here, your J bar is becoming 0 if I'm using a magnetic scalar potential. It is restricted to only, so I can use a scalar magnetic potential only in the region where the current density is 0. Then only I can apply this scalar magnetic vector potential. So we are restricting ourselves. And that is why now what we are doing is, so we have applied it to the Ampere's law, and we got that this is our restriction. Then we are applying here. What is this one? So this was the first law of magnetostatics, Ampere's law. And this is the second law of magnetostatics, which is, what is this law? Can anybody tell me? Yes, Hassan al-Musallam, can you tell me what is this law? Differential form. Mr. Hassan al-Musallam, you are there?
Yes.
Yes. What is this law? This is the differential form of Ampere's law, right? So what is this law? We have just now studied this, Hassan. We have just now studied this. Yes, can anybody tell me what is this law? Yes, can anybody tell me what is this law? What is this one?
Gauss's
Ampere's law.
Gauss's law. Just now we studied. It is Gauss's law of magnetostatics. Magnetostatics. It's the Gauss's law. Closed surface integral b bar dot ds bar is equal to 0, or del dot b bar is equal to 0, or I would say del dot h bar is equal to 0 over mu, which is 0. The Gauss's law. So for this restriction, for j is equal to 0, now if I substitute my magnetostatic potential in the second law, it's fine. I'm seeing the Laplace equation, Laplace del square Vm is equal to 0. And if you remember, this is applicable in the charge-free region. In the free regions, it is applicable in the charge-free region. That means there should not be any charges or any current, which is correct. So this is restricted, and therefore we are getting the Laplace equation. So this is fine. So your Ampere's law and your Gauss's law, they are okay, but the restriction is that your current density must be 0. So therefore, now we go to the another method. We go to the more generalized method. So what we do is, rather than working with restricted, conditions, we go and we define the magnetic potential as a vector quantity. So we defined a magnetic potential as a vector quantity. See, as a vector. We defined a magnetic vector potential, not a scalar, because we have just now seen in a scalar, it is a restricting us only applicable to j is equal to 0. So therefore, now we are going to a more generalized solution where we are defining the vector potential as a vector, the magnetic potential as a vector, and it is defined as A bar. And this magnetic vector potential, we are defining it in this manner. B bar is del cross A bar. That is, the magnetic flux density is del cross the magnetic vector potential. Okay, we are defining it in this way. And you will see we are defining it in this way because if we use this way of definition, then both our Ampere's law and our Gauss's law will hold. So there will not be any inconsistency. So we define the magnetic vector potential in this manner. So therefore, first, we are checking whether this definition of magnetic vector potential in this manner, whether it will hold or not. We are first applying it to the Gauss's law. Del dot B bar is equal to 0. Put it here. Del dot del cross A bar is equal to 0. Correct. Divergence of curl of a vector field is 0. Vector identity. Okay. So it is satisfied. Okay. Now we are going to the next one. So therefore, as I told you, so we have two type of potentials, scalar and vector. So now we are using a vector potential. Now we got this one. Now the second one. The second one is our Ampere's law. So we are now applying to our Ampere's law. So del cross H is J bar. So H is B over mu. So mu is coming out. So del cross B bar is equal to J bar. And del cross B bar is mu on the right hand side, mu J bar. And now I'm substituting B here. So del cross A is equal to mu times J. And what is the vector identity of del cross A? Is del of del dot A bar minus del square A is equal to mu J. So I'm getting this as the end answer. So first we applied to the Gauss's law and we saw that our definition of magnetic vector potential as del cross A is good, intact. Now I'm using Ampere's law and I'm checking whether I'm getting the Poisson's equation or not. So now I'm getting this extra term here. See this extra term here. I'm getting this extra term. Now, the good thing is mathematically, our magnetic vector potential is not unique. That means the magnetic vector potential expression is not unique. So it is always possible that you select a particular magnetic vector potential expression such that it satisfies del dot A bar is equal to 0. So when it satisfies del dot A bar is equal to 0, that means this left-hand term will go to 0. And what we see is this one, which is del square A bar is equal to minus mu J bar. And this is called as the Poisson's equation in our magnetostatics, where we know that in our magnetostatics, the source is the current. So that's why the right-hand side, which is the source, is the current, J bar. And whereas in electrostatics, we had del square V is equal to rho V over epsilon. Am I right? This is what we got. So here for electrostatics, the source was our charge or the charge density, which is on the right hand side. And left hand side, we had our potential. We had our potential. So here also the source, which is our current density, and the left hand side is our potential. So this is the Poisson's equation. Of course, this is in vector form. This is in scalar form. Okay. So this is how the vector magnetic potential is defined. And we have seen that by defining the vector magnetic potential as B is del cross A, we have assured that the Gauss's law of magnetic field is satisfied, which is del dot B bar is 0. And also the Ampere's law is satisfied. And we have seen that from the Ampere's law, we got the correct Poisson's equation by making sure that del dot A bar is equal to 0. And remember, you know, in mathematics, this is all our mathematical way of representing. So remember, your magnetic vector potential must satisfy this. It must satisfy this. So, you know, this can be a good way of checking if any potential given to you is a correct magnetic vector potential or not. So if suppose you are given, you know, 5 different vector fields, 5 different A's, you know, A is equal to this, A is equal to this, A is equal to this, A is equal to this. And you are asked out of these ones, which one is the correct magnetic vector potential? Then you can use this idea, because this must be satisfied in order to select that answer. Suppose if this satisfy, in order to select, if this satisfy, that means this is the magnetic vector potential which is applicable to our magnetostatics, because it satisfies this, and therefore I will get this as the Poisson's equation. Okay, so this is the magnetic vector potential. And now let's just spend a little bit on this magnetic vector potential, because now it is in vector form, right? If you see, guys, this is in vector form. So it is in vector form. So let us just consider a simple Cartesian coordinates, and we just write this magnetic vector potential. We just decompose them for the X case, Y case, and Z case. So I am decomposing the vector Poisson's equation to scalars. So I have 3 scalars. So del square AX is minus mu JX, del square AY is minus mu JY, and del square AZ is minus mu JZ. Now, how I can get AX? How I can get AX? Now I'm just using an analogy. Okay, you can go and you can solve, but here I'm using analogy. And what is that analogy? By the way, guys, so it is del square V is minus rho V over epsilon. I'm sorry, in my previous discussion, I just used rho V over epsilon. So in the video, you know, rho V over epsilon will be recorded. So please correct, it should be minus rho V over epsilon. So this I'm borrowing it from electrostatics, that if this is my Poisson's equation, del square V is minus rho V over epsilon, then I get the potential V as integral over V, rho V dV over 4 pi epsilon R. And because remember, this we derived the potential due to any, you know, we started with point charge and then we generalized it to line charge, surface charge, and volume charge. So I'm taking the more generalized case, the volume charge. So if this expression is giving me this as the solution of my potential in electrostatics, then can I use the same analogy? And can I say that in my magnetostatic, if del square AX is minus mu JX, see here, so rho V is replaced by JX and 1 over epsilon is replaced by mu. So rho V is replaced by JX and 1 over epsilon is replaced by mu. This is in electrostatics. This is in magnetostatics. Then therefore, I can get AX as integral over V. Rho V is JX. Rho V is JX dV over 4 pi epsilon. So epsilon will be 1 over mu, because if 1 over epsilon is 1 over mu. So 1 over mu means it will go to the numerator. So AX is integral over V mu JX dV over 4 pi epsilon. So this is how you can get the X component of the magnetic vector potential. Similarly, you can get it for the Y component and you can get it for the Z component for the magnetic vector potential. And if we look at the direction of the magnetic vector potential, if we look at the direction, so this is X, this is Y, this is Z. Now, can I write it in the vector form? Because my Poisson's equation is in vector form. So therefore, I can say if this is my AX, this is my AY, and this is my AZ. Therefore, my A bar will be equal to integral over V in mu. It is J bar now. JX, JY, JZ, J bar dV over 4 pi R. This is for the magnetic vector potential when I have a volume current. That's why it is J bar. Now from here I can get, if it is surface current, then J bar can be replaced by K bar because K bar is your surface current. And for the line current, it will be IDL. It will be IDL. Your K bar DS will be replaced by IDL. So this is the expression of the Ampere magnetic vector potential for the line current. So it is integral over L mu I dl over 4 pi R. Okay, mu I dl over 4 pi R. Now, this question is open. Can anybody tell me, because now your magnetic vector potential is a vector quantity, so we need to think about its direction. Now looking at these, can anybody tell me what is the direction of the magnetic vector potential? In which direction your magnetic vector potential will be? In which direction it will be?
The direction of the current.
Exactly, very good. So if you see here, it will be the direction of the current. If you see the left hand side and right hand side, your magnetic vector potential will always direct, or its direction will always be the direction of your current density, or the surface current, or the line current. So this is what the magnetic vector potential is. So therefore, now your magnetic vector potential, we have checked, it satisfies the Ampere's law, it satisfies it satisfies the Gauss's law, it satisfies the Ampere's law under the condition that del dot A bar should be equal to 0. Therefore, we use magnetic vector potential for our magnetic fields or magnetostatic cases. And the direction will always be the direction of the current, because your A bar will always be parallel to the line carrying current I, or the direction of the current. If the direction of the current is in this direction, then A bar is in this direction. Okay, So this is the magnetic vector potential definition. And now, since we know B bar is del cross A bar, now can I just find the magnetic flux psi, which is the surface integral B bar dot dl bar? Can I find it in place of the magnetic vector potential? Yes. In place of B bar, substitute del cross A. So del cross A dot ds. Now, if you apply Stokes' theorem, convert the surface integration to line integration, we know that the surface integration of del of any vector field ds is equal to the closed line integral, the vector field dot dl. Sorry, it should be dot here. And therefore, your flux is nothing but the closed line integral, the magnetic potential. So you are evaluating the magnetic potential over a closed line will give you the magnetic flux. So this is also correct. This is also correct. So if magnetic flux density is given, you can use this expression. If the magnetic vector potential is given, you can use this expression. Okay. So this is the magnetic vector potential. And you have a simple example here. So you have your A magnetic vector potential is given to you, which is rho square Az Weber per meter. By the way, as I forgot to tell you, the magnetic vector potential units is Weber per meter. And now you need to find the flux through this rectangular area. So how do you find the flux through the rectangular area? If A is given, you can find the closed line integral A bar dot ds. So you just find what is the path which is enclosing this area. So this is the path. And evaluate the line integral over this path, and you will get the answer. Okay. So I think we will stop here. And in the next class, we will take this. We will spend 1 minute more on this example, and then we will go to the magnetic forces. Okay. So thank you very much, and we will meet on Sunday.
Doctor,